Hello everyone and welcome to Vibrations in Acoustics. Today in this problem what we're going to do is find the equivalent mass for this system. So we have basically like an oil rocker, oil donkey or something like that, that's being driven by a cam. It has some mass hanging off of here. It has some mass in itself with some moment of inertia. And then it has another mass hanging off this side. So you could think of this as like one of those oil pumps you see in the Midwest all the time. Alrighty, so what we're going to have to do here is we're going to use the energy method to figure out the equivalent mass at the point A. Now, the location where you choose to have the equivalent mass is really important because it's the things like JR and MR and all this kind of stuff are going to be affected by where you place the equivalent mass that you want. Okay, so using the energy method, we're denoting kinetic energy as T. So if you haven't seen this notation, Ke is equal to T, is equal to 1/2 this mass, MP, times its displacement squared. Or no, it's velocity squared, I'm sorry. 1/2 mv squared. So since MP is moving at the same rate as xp, you multiply it by xp dot. Okay, so then plus 1/2 mr times x dot r squared. Now you may notice that we don't really have an xr defined anywhere in this picture. That's because it's not defined. This value is going to be related to theta r with respect to A. But we're just calling it xr right now because it's going to be the displacement at A of this rotational arm right here. Okay, so then plus 1/2 JR theta dot R. I'm not forgetting something, am I? I don't think so. Okay, yes. Oh, sorry, I had a message there. Alrighty, JR, MR. Okay, so yes, you have, since you have it. Since you have the rotational body with a certain mass, you have the inertia, which creates basically a mass in motion that you have to account for, which is JR, and you also have MR, which is the actual mass of the body, moving in the translational direction. So you have a rotational mass and a translational mass, basically, is what this is saying. Okay, so then, moving on with this, hopefully nobody else bothers me, times mv times xv dot squared. Okay. So, we have all of the masses and the inertias defined. Now what we can do here is we have to get them all in respect to xp, or xp dot, depending on how you look at it. So, what we do here is, let's start with A. A has a displacement of xp dot, or a velocity of xp dot, which we're just going to call x dot, just to make it simple. Alrighty then, so if we move on to xp dot, xp is a relation to how far theta is times the length. So xp is equal to theta dot r times L1. Because we're basically saying it's a small angle, and at a small angle the displacement of xp is just going to be theta times L, because sine, or in this case it'd be sine of the angle. If it's a really small angle, it's basically the same as just the theta times the angle. Okay, so this is equal to x dot. So then theta dot r is equal to x dot over L1 by just solving out this equation. And now we have theta r in respect to xp or x dot, whichever one you want to call it. Okay, so then xv is equal to theta dot r times L2, the distance across here, times the theta r, which is then equal to L2 all over L1 times x dot. Because of the theta r we already defined as this, so we just stick this down in here. You have L2 over L1 times x dot. Okay, and then xr, my v and my r kind of close together there, x dot r XVR, is equal to theta dot R L3. So this is basically the location of the mass, is the center of gravity right here. So this is where you would say the mass is. Okay, so then this is going to be equal to L3 over L1 times x dot, by the same logic of theta r coming right here and being subbed in here. Okay, so now we have all our displacements with respect to xp, so now we can find the equivalent mass about xp using the energy method. So substituting in these values for theta r and xv and xr into this equation, we're able to go through here. Notice I had xr defined at the center of gravity. That's where you consider the mass of this entire thing, even though it has a moment of inertia, basically, J, an inertia over the entire body. But you count the center of gravity as the location of where the mass is used, if you didn't catch on to that. Okay, so then T is equal to 1/2 mp x dot squared plus 1/2 mr x dot squared of L3 over L1 squared plus 1/2 jr of x dot over L1 squared plus 1/2 mv of L2 over L1 squared is equal to the equivalent system, which is 1/2 the equivalent mass times x dot squared. Okay, so now we can cancel the x squareds. X dot squared, x dot squared. Oh, forgot one x there. X squared. There we go. Cancel that, cancel that, cancel that. Also cancel all the 1/2s. And that should pretty much do it. So you have the mass equivalent over here is equal to mp plus m r times L3 over L1 squared plus jr times 1 over L1 squared plus mv over L2 over L1 squared. And that is your equivalent mass for this little oil derrick or oil donkey. Basically, you just have to make sure that you find the displacement, hence the velocity, the derivative of the displacement, all with respect to this A, to the point where you're trying to find the equivalent mass. And then you use the energy method, the kinetic energy of each one of those masses, times that velocity, and then you solve for MEQ.